thank you for coming out tonight. I don't know what you're missing on TV, but I watched an interesting landing of some astronauts and a cosmonaut that dropped down. They actually hit the water at 5:10, and it took them about 40 minutes to secure the capsule onto a ship and then help the astronauts come out of the capsule, because Earth's gravity makes their arm feel like it weighs 800 pounds. So they needed some getting used to there. You can put some chairs down wherever you want if you want to join us here. I learned my first experience with cratering from a guy who was probably at that time the world's leading authority on craters, Eugene Shoemaker, who many of you have probably heard of. Well, he was an adjunct to our university from wherever he worked permanently. I think was Arizona State, something like that. And he was in the northern Illinois area to see a relative and stopped by the university and said, sure, I'll give a program on cratering. So this is quite different than he gave, but that's where I got the urge. Okay. So we're talking impact cratering, and please be aware that although this is an astronomy club, there's going to be about equal parts of physics, astronomy, a tad less of chemistry, and geology. A lot of geology in this, because it's usually the geology you're studying, millions of years after the fact. So you see here, Meteor Crater or Barringer Crater, Arizona, which is an absolutely stunning place to visit for about an hour or two. And I told my wife it's absolutely fascinating that the crater hit so close to the gift store. I mean, within just a few hundred feet. It was amazing. Okay. More than once, people have asked me, well, who wants to go see a big hole in the ground? Me. And impacts are much more important than most people realize. It's not just geology, it's also biological history and mass extinctions and things like that that are very important. We also know that there are some major ore deposits associated with many craters, not all, but many of them. We have huge quantities of igneous rocks, and if you were to go to the Colorado Plateau or the Deccan Peninsula in western India, or Siberia for that matter, there are thousands and thousands of feet of lava flows, and these are related to nearby volcanic, I want to say eruptions, but they're fissure eruptions, which means they may be erupting along a crack that's a mile long. It's not the typical single volcano that is spewing it out. We also know economically that major ore deposits, and I'll get more on this when I talk about Sudbury in a few minutes. So we have at least one major biological extinction, quote, the dinosaurs, and probably several more. We'll take a look at that also. Now tonight, as you can see here, I'm going to explain the physics of impact craters, what processes shape them, and those that destroy them. I'm going to provide you about 8 different kinds of evidence that it is impact, not volcanic, that forms most of the craters, and how they can be used for dating planetary surfaces. I will use Eugene Shoemaker's joke. Some of you may not be as excited about dating as I am, but I preferred girls. No, I'm sorry, it was his joke, his joke. And estimate the odds of a possible major impact on Earth. That's one of the last things we'll look at here. Here's what we see when we look around the solar system. Craters are everywhere. Every moon, solid surface planets, that would be the Earth-like or terrestrial planets. But when you get out to the gas giants, you're looking at their satellites, not them, because it's just a ball of gas. But their satellites, all the way out to Triton, which is Neptune's biggest moon. There are hundreds and hundreds of craters. So something rather dynamic happened early in the formation of the solar system. We also know that there's lots of things on Earth that are trying its best to hide these from us. So we have weathering and erosion and glaciation and plate tectonics and all of that sort of thing. They tend to obliterate, especially the older ones. If I'm in your way, yell, I'll get out of your way here. Okay. Now we're starting with an assumption that has been verified by most astronomers, that solar system formation is a concept gravity driven that creates an object in the middle, which would become our sun, and an accretion disk that is orbiting the same direction that the sun is rotating. And essentially that's how we photograph other areas. I'm thinking now the Orion Nebula. There are many, many solar systems in formation very early, but they all seem to have a glow in the middle where the mass tends to accumulate and form whatever star is going to be there, and then the swirling disk of dust and gas that becomes the planets, asteroids, comets, you name it. We also know from observation it doesn't happen as often now as it used to. The last one that I remember was quite memorable was Chelyabinsk in Russia. And the one thing that is really dangerous to do, everybody in town did exactly the wrong thing. They see a blue light coming down from the sky, and they rush over to the windows to look out, and after the shock wave broke all the windows, something like 1,800 people in that town were admitted to the hospital due to cuts by glass. So what they should have done is just hide and then ask somebody, what did you see, if they weren't being carried off by an ambulance. Okay, this very complicated looking chart is not so complicated when you break it down into everything here is a geologic period. Okay, and this is the number of years in millions that we're going to start, and we're going to come up to the present at 0, 0. Okay, so today is 0, 0. It is not important that you learn any of the names of the geologic period. That's the first major quiz in a geology class. However, the y-axis here is the diameter of the crater. So that's a little bit different than some of graphs like this. Every one of those colors starts with a small, I don't know, 5 miles or something wide, and it goes on up, and it will tell you the period that it happened. Okay? And of course, we all know there are a couple more important than others. What is called, or used to be called, the Cretaceous Tertiary period, which is over here somewhere. Jurassic, Cretaceous, that's what I mean. Jurassic Cretaceous is the one that we know an object about the size of, say, 6 miles across, 10 kilometers, hit, and the damage done wiped out the dinosaurs as far as we know. Okay, there's lots of different codes on here you don't need to know, but there have been mostly biologists who studied these lines. They have to know something about the rock they're dealing with. So in the group somewhere, there's liable to be a computer expert, there's going to be a historical geologist or a petrologist, somebody who knows rocks, and then the biologist can put it all together. And if you see a line that stops right here, that means there's no evidence from that point in time toward today up here. So you can actually date when most of these catastrophes did happen. And there are far more of them than most people are aware of. Here's a KT. That's one big one right there. And that caused the Chicxulub crater, among other things. So there's lots of stuff on there. Just remember, you're not geologists. There's no quiz on it, so don't worry about how long ago it was. Virtually everything is less than 600 million years old. Why? Because it's largely been wiped out. Too many years have gone by. The craters are difficult, if not impossible, to find. That's why Geologists do a lot of drilling to find this stuff out. Okay, when I was going to school, actually got my bachelor's degree in 1970, we were taught that it was either volcanoes or impacts that formed the craters on the moon. Well, about 2/3 of the people favored the volcano, and that's because there's a lot of geologists around, and about 1/3 favored the impact origin. Okay, we had to wait until the Apollo program brought back 840 pounds of rocks, some of which were dated in a physics lab, actually in 3 different physics labs, to get dates on these things. And there's 2 terms that are going to be thrown out here. These are geology terms, but it's real simple to understand. Absolute dating gives you a date, which is based on radiometric decay. And when you use 3 different elements, A decays into B, L decays into M, and X decays into Y. And if they all agree on the date, you're pretty reliable with that date. The other kind of dating is called relative. No, we're not talking about taking out your sister on a date. Relative dating just simply says, I am older than you are. That doesn't say anything about how old you are. It doesn't say how old I am. But compared to her, I am older. I'm 79. How old are you?
None of your business.
Okay, good answer. Excellent answer.
But I'm younger.
Okay. I'm going to introduce you to a term now that, unless you've had a physics class, you may have never heard before. The unit that is largely used to measure pressure is called a Pascal, and its abbreviation is PA, after a French scientist, okay? These impacts that come down go way above what you might think in the way of pressure. So I would like you to imagine a card table. You probably have it in your front closet. It's about 40 inches wide on the side, 4 legs, play cards on it, have fun, right? We're going to take a mass of 1 kilogram and put it right in the center of the card table. That is about the definition of a Pascal. It's 1 kilogram per square meter. So it's very close to that picture you might have in your head of a card table. That is a Pascal. However, it's almost too small to even mention in here. So we're going to use some prefixes, okay? When you get up to 1,000 of these weights on the card table, ignore the fact that it would collapse, okay? 1,000 kilograms is called a Yes, a kilopascal, that's exactly right. KPC is the abbreviation, kilopascal. Now we multiply that by 1,000, we get a mega, which is 1,000,000 of these little 2.5 pound weights called a kilogram. And now the floors collapse probably, and maybe into the basement. But we're not done yet. We're going to multiply that by another 1,000 because we're talking 1 billion. And that is the lowest level of metamorphism to determine in these craters. This is 1 gigapascal or GPA. And as you can see here, this is a zone where there's at least 5 gigapascals, 10, 20, 50, and in this innermost dip, it's 100 gigapascals. So that is incredibly, I mean, making artificial diamonds doesn't take anywhere near that level of pressure. And for this instance here, we're going to pretend that we have a 10 kilometer per second collision with the Earth. In reality, the best way to imagine that, the Earth is orbiting around the sun at about 30 kilometers per second, and something comes in from behind and hits it at 35. That's going to be a pretty minor bump, the difference only being 5 kilometers per second. It might ruin your car, but it's no big deal. So when we use an artificial number like 10 kilometers per second, please be aware that a head-on collision can occur at somewhere in the ballpark of 70 kilometers per second. Okay, much, much faster. If you'd like to know what 70 kilometers per second converts to miles per hour, kilometers from 70 would be you divide by about 0.6. So that's about 4, and we'll round it down to 4 miles, okay? And going from seconds to hours, we multiply by 3,600, with 60 seconds per minute and 60 minutes per hour. So now we've converted kilometers per second to miles per hour. And that number would come in somewhere near 72,000 miles per hour. That is massive. That would be a head-on collision. I'm not sure why Bevan French, who created this diagram, used a number that's that small, but it'll work. Okay, now we go to the right-hand side of this diagram. We're going to start above 100, that would be 100 gigapascals, the rock is vaporized. And it's just going to be ejected out in some ballistic orbit and land somewhere or mix with the atmosphere for a while. From 50 to 100 gigapascals, the rock is totally melted. Then we have a zone that drops down to about 5 gigapascals, where the rock is metamorphosed. And I'll show you several different types of samples that would come from that area. And then lastly, rock is cracked, and the term brecciated, I'll also spend some time on that. But this is a cross-section of the kind of pressure involved when an object hits the Earth. Okay, bear with me, I've got a couple slides here with a lot of text. The very first thing that happens, the atmosphere doesn't slow it down very much. I mean, it's going through 70 miles or 60 miles of atmosphere in fractions of a second. The contact compression stage, the microsecond that the leading edge of the impactor touches the solid ground. You put it on a stopwatch. The impactor is completely stopped within 1 to 2 times its own diameter. So something 10 miles across will not get deeper than 20 miles. Okay? We've got 2 hypervelocity shock waves are produced, and the first is directed into the surface rock. Of course, that's what's doing the damage, which will create the crater. And the second, Newton's law of action and reaction, is directed back into the impactor. The shock waves lose energy and rapidly as they move away from the impact site. And there's some additional loss of energy due to heating, deforming the rock, and accelerating a surface rock, which will go out and basically land to form the rim around the crater. So we have rings of shock deformation. And depending on the pressure there, like I say, we're talking total vaporization above 100 gigapascals. The rock, we have a zone there of melting rock. And again, a given distance depending on the impactor's mass and velocity, the rocks transmit this energy as elastic or seismic waves. So with that term, I know all of you have heard and studied a little bit about earthquake waves, but they produce 3 types of waves. The first one is the fastest. It can go around the crust at approximately fast. Okay, I'm rounding off here, very fast. They actually go about 18,000 miles an hour, those first waves. Then the second waves are delayed a bit because they move differently. They're not compressional, they kind of wave back and forth. And the third one is something that actually causes the entire ground motion. L waves are long waves. So the difference in the waves does a lot of damage, especially to buildings, etc. Okay, by the way, I am getting most of the information for this program from 2 people. Bevan French, who is an astrophysicist, who is an expert on cratering, and Eugene Shoemaker, who approached the concept differently, but has worked magic with what we understand how things work. Okay, so the shock waves race outward in all directions, including back up to the surface where they're reflected again back down. The energy always produces a symmetric excavation, and tests have been done that it doesn't matter what angle an object hits the Earth or another planet, as long as it's greater than about 6 degrees. 6 degrees and lower would be a skid that instead of a circular crater will actually produce an elongated trough of some kind. It's even possible that an object will bounce off the Earth and keep going out into space. Okay, so above the shock center, waves moved outward and upward. Below it, they moved downward and outward. And the result of all this, which happens in a few seconds, is a bowl-shaped excavation called a transient cavity. Fancy words. As soon as that is created, and as soon as things stop falling, so to speak, then you can go back up and take more look at the step-by-step how that happened and what the results are. And this is where Shoemaker comes in. Now, as a geologist, he's going to be looking for different things than an astrophysicist, okay? If you're out walking around in Nevada at some of the nuclear test sites from the 50s, etc., he would not know what kind of rock is out there. The geologist would. So we've also studied rocks brought back from the moon, which show intense metamorphism unlike anything near any volcano on our planet. If you're not familiar with a railgun, it is an object that accelerates a mass, like maybe a steel ball would be one example, and it is fired electrically, I guess, and they can get up to speeds of several kilometers per second, faster than a rifle bullet by far. A typical rifle bullet will go about 1.5 seconds to go a mile. So that's very slow compared to a railgun and what it can produce. And this isn't necessarily important, but looking at what happened, what kind of damage was done, that's where these guys excelled and came up some very interesting ideas here. The layering of rock at Meteor Crater in Arizona resembled patterns that were observed in Utah by Shoemaker, and they were caused by underground nuclear detonations. And he determined that what happened to a lot of that stuff is the layers of rock on both sides were flipped upside down and deposited. So if you're going through the rocks, you're repeating some because it got flipped upside down. That's what they saw immediately at Meteor Crater when he was studying it, probably in the 70s, that's my guess. Don't quote me on dates. And everybody knows if you look at the moon, some of the craters have light streaks moving away from them. Those are called rays. And the rays created by impact cratering are visible. They were not formed through any known volcanic process. And we're also going to look at collapse features inside the crater that are known as terracing. And again, the terraces are not found in volcanoes. They are only found where there are impact sites from asteroids, comets, what have you. And again, we're going to look at the very special kinds of minerals and rocks you find that are associated with meteor craters. We already had a talk on this about, a year ago maybe? A guy was talking about the Tunguska 1908 collision. And he did not draw conclusions as to what hit the ground because it's not known for sure. But here's some things we did discover about this. There's no crater. There's no magnetic anomalies caused by iron if an iron asteroid hit the ground. They go back and forth with gravity meters, and there's none of that. The trees are laid down nicely. I think it's about 1/3 of a mile, this blast, that the trees are all radially laid down outside. But nobody knows what hit the ground, or if something did hit the ground. I know some of the Russian scientists, 30 years after the first proposals, so somewhere in the 40s, proposed that it was a comet that completely vaporized before it hit the ground, but that energy still hit the ground. And of course, ice is going to sublimate, disappear, and become part of the atmosphere. There'd be no evidence left behind. And that may be the best explanation, but nobody's for sure. When this happened, of course, you couldn't get out there. The USSR was one huge swamp. Every time the 3 largest rivers in Russia all head north, when they flood in the springtime, the ground is soaked. You'd have to be some kind of a very large, flat-footed creature to walk without sinking in. It's a mess. There were no roads. There were no railroads until the Transcontinental Railroad was finished, and I do not know the date for that. But it was a long time after 1908 that Russia's first scientists got out to study this. So I'm going to go with the comet for the obvious reasons. There's a lack of crater. There's no evidence anything metal hit the ground or stone or anything like that. And if you have to drill in the right place to hit that evidence, they've gone over it with magnetism and everything else. They're still not sure. Now, these two rocks were originally quartz, like maybe the rose quartz you have out in your garden. It's a real simple silicon dioxide rock, and it's very beautiful, okay? However, you squeeze it with gigapascals worth of pressure, and you can get some very strange metamorphism inside the quartz. For instance, here we have one set of structural planes running off this way and another set over here. And it's rare to see two different angles coming together inside a rock. So the lesser of the metamorphose is called coesite, and the greater of the metamorphose is stichkovite, both forms of quartz. And here we have planar deformation features. You see these large stripes going down from top to a little bit to the right, not straight down, but down and to the right. But in between them, there are all kinds of oppositely structured cracks in that rock. And that kind of planar deformation requires tremendous shock because quartz is a very hard rock. And the hardest rock I know of in the world is just north of us. There's a state park up there that has lots of this good stuff. It's called quartzite. Some of you may have it around trees in your yard for landscaping. Quartzite is simply the crystals of quartz all grow till they run into each other, and then they lock crystalline together. You can't break a piece of quartzite with a hammer. It is that hard. Now, there are minerals that are harder, but that's the hardest rock I know of, and I have a minor in geology. Here is something known as breccia, and what we're saying formed this. Look at every one of these inclusions. They have very sharp angular pieces to them. You don't find any nicely rounded pebbles, which you would get if water laid it or it was in the vicinity of the surf zone of a major lake or ocean. No, these are glued together, fragmented rocks, and that's what you call breccia. It's not hard to find if you look in the right place. Some of this stuff was blasted from impact sites more than 100 miles away. And we have an impact site less than 100 miles from right here. More on that later. You want diamonds? Yes. Nanodiamonds are also found all over areas that have been impacted. Now, what is a nanodiamond? It is a, quote, small diamond. However, look at the smallness to it. How many of you know, show me hands, what an angstrom is? Good. For those of you who don't speak metric, an angstrom is 10 times smaller than a nanometer. Okay? So it's 10 to the minus 10th meters rather than 10 to the minus 9th nanometers. And here's an area where there are diamonds, but trying to get that out, and you'd need an electron microscope even to see that stuff. It's so tiny. But they're there. I want to thank Frank here for turning me on to this particular type of rock. You mentioned a place in western Arizona, Western Australia, that had a probable, has not yet even now been confirmed, but it's very probable, had an impact crater that was close to 300 miles in diameter. Chicxulub was 110 or something like that. But this is a rock. Imagine a traffic cone. It's small at the top, and it gets larger as you go down. That's what this is, and this is the flat bottom, so the top would be off the slide over here. Shatter cones, found nowhere near volcanoes, but very common in impact zones. And of course, we must talk about Buckminster fullerite. That is a mineral made of buckyballs. This is carbon 60, And carbon-60 hooks together to make it this round ball shape. You don't find these anywhere. They're very small, and they're in the area of impact sites. And then again, we have a very interesting rare earth element called iridium. And if you have a periodic table handy, you'll find it near platinum and gold on the periodic table. Element 77. It is far more abundant in asteroids and comets than it is on the Earth's surface. And the iridium content decreases the further you are away from an impact site. How many have ever heard of Lewis and Walter Alvarez? Good. Glad to see a hand. Lewis Alvarez was a Nobel-winning chemist. He and his geologist son Walter were some of the first people to study the KT rocks and determine, this was an impact. And once they calculated the energy, they understood why the damage was done that way. But Nobel Prizes aren't given out, for being popular. These guys really knew their stuff. Okay, so we have a little iridium anomaly, and that is always going to be associated with the death of the dinosaurs. Iridium, remember that element. Now here's a simple geology lesson, but it adds some of the stuff we've already talked. This is temperature going up this axis in Celsius, and this is pressure in gigapascals going up to more than 100. These are common metamorphic rocks in mountain building regions where great pressure from plate tectonics is forcing rocks upward, bending them, doing all kinds of stuff. All of these are, I have a beautiful piece of blue schist at home. Just because I always like the response when somebody says, "What's that?" and they say, "Just a piece of schist." What? Blue schist, yes. Normal metamorphism. Sphene melts, quartz melts. This would be roughly 1800 Celsius. That'd be about, give me a second, about 3,200 degrees Fahrenheit. And zircon decomposes at even higher temperatures. Notice there's nothing up above here. Everything else would be melted away. Drew, can you explain for a second why you were picking zircon crystals out of piles of other stuff in the research you were doing?
Because they don't decompose.
Exactly. They're very hard. They don't decompose. They last literally forever. Okay? That's not quite true, but zircon is one of the hardest things that you can find on the planet. And it contains a lot of information about where it came from, maybe where it formed with regard to the solar and maybe the pre-solar nebula. Okay, now we're going to crank up the pressure. And when we get up to a little past 2 gigapascals, we get graphite and diamond. And the only difference between them is the pressure that was applied. You get graphite out of a pencil. That's all it is. Then we have quartz, coesite, and stisovite. That's, again, different pressures on the quartz itself. We get shatter cones, planar deformation features, diaplectic glass, melting, and over here, over 100 is vaporization. So this happens in extremely rare cases, but it happens. Now I'm going to do a little experiment. I'm going to ask you to reach into your pocket or purse and pull out some coins that you might have in either pocket. I don't carry coins, so I can't do it. I throw them into a bucket at home.
How about a credit card?
Credit card will not work.
Keep in mind, please, there's so much metal there.
Okay. You want to give that an explanation, Jack? You seem to know what she's got.
He gave me a nickel.
That's good. Those of you who are holding a nickel in your hand are more likely to be holding a piece of an asteroid than anything else. Why? The United States, over the last 30 or 40 years, has imported greater than 95% of the nickel we get in this country from Sudbury, Canada. They're real close. We're good friends. At least, let's just say we used to be. All right, hopefully we'll be friends again. But this is a geologic map of the Sudbury district. That's not important. What's important is all of the mineralization that is found in here, copper and iron. There's some silver, not a lot. Nickel, tons of nickel, megatons of nickel. And when they date this, this structure is the oldest, seems to be in the middle. And it's not a mountain, it's not a hole, it's sort of level, but the center is a little bit lower than the rest because of erosion. That's where nickel was brought in, probably by an iron nickel meteorite. Bang, hit Sudbury, and it's been mined and been a nice place for people to visit. I've been there once, but I was so young I didn't have an idea what I was really looking at. I think I was 12, but that is still a cool place to visit. Sudbury, Ontario, Canada, which maybe 80 to 100 miles north of Lake Huron, not too far up there. So remember, the next time you pull a nickel out of your pocket, you're giving away an asteroid. At least, probably. Now, what an astrophysicist is interested in, and some geologists, is what kind of energy does it take to do the damage that is being claimed here. I have about a 5-step thing. It's real interesting. Number one, you have to ask the question, how much energy is produced by a typical impact? It's a very simple formula. Take 1/2 the mass times the velocity squared, and that square makes all the difference in the solar system. So we're going to go here and make up an example. The mass of a typical 30-meter, that's an iron nickel type meteorite, is equal to a freight train about a mile long. One meteorite, a mile long freight train. And the velocity of that typical meteorite in the inner solar system is about 50 kilometers per second, much faster than the original diagram I showed you, which was 10. Okay, 50 kilometers per second and a mile long train. Here's our energy. Please read it. You got to get that train going at 43,000 miles an hour to have the same impact energy as a 30-meter iron nickel meteorite, in case you were wondering. Now, I've underlined the important thing in that paragraph. Virtually all of the dating of the surface of the moon and Earth, when we can get to something that old, gives us a very narrow window considering the Earth is 4.6 billion years old. All the cratering throughout the entire solar system, we believe, started 4.2 billion years ago and stopped about 3.9 billion. That's 300 million years. No one knows exactly why all the cratering happened. Some people have postulated that there used to be a planet where the asteroid belt is, and it blew up. Well, they haven't explained it. There's no evidence for that, but it might have been. It's just simply more likely to be a swarm of asteroids that hit in our solar system and is no longer available in our solar system. Okay? The nickname for this time period in geologic history is the heavy bombardment period. And it occurs everywhere in the solar system out to Neptune's largest moon, Triton. There is no object that isn't cratered unless it's been resurfaced. And when you talk about Io at Jupiter, there's so much volcanic activity there you can't really see most of the craters as they're already buried under fresh lava. So why weren't we hit? We were. 70% of anything incoming would have hit oceans because we're about 71% water and 29% land. And since that formed, whenever that was, we have a whole bunch of activity here that is going to destroy the evidence of craters. But they still exist, especially the younger ones. And here's something, I don't really appreciate history. I probably should appreciate it more than I do, but this caught my eye as I was reading a book. It was in one of Carl Sagan's books, by the way. True story, in 1178, a Canterbury monk claimed to have witnessed an explosion on the moon. He described it in his journal as an explosion just behind the upper right edge of the moon. That'd be at about the 2 o'clock position if you think of a clock face, okay? And it resulted in showers of debris raining down, causing a blurring effect for several hours over the entire moon. No one else saw it, but he wrote it in his journal. Okay, maybe we can test that theory. NASA discovered where this would be, and they purposely photographed that area, and son of a gun, they found a fresh little 20-mile wide crater, and they named it Giordano Bruno. I won't go into the history there either. But physicists say, well, that doesn't prove that that was the object that caused what the monk actually saw. So physicists determined that an impact that was only 800 years ago would leave the moon still ringing like a bell. So they decided they could test this theory. If it's ringing, the crust is moving up and down several inches a second, or whatever the period is. And when they tested that, the mirror device built by the French called a retroreflector, whatever angle a laser beam hits it, it sends it back in exactly the same angle. Well, at the McDonald Observatory in Texas, they pulse lasers off of these. They know exactly where those mirrors are on the moon, and they pulse them like every 1/10 of a second. They'll hit it, and then they'll pause for a while, and they see the result. The light goes there and comes back, and if you map the returning signal, it's getting shorter, then it gets longer, then it gets shorter and longer like a bell. It's still ringing. And the physicists said, well, we have no other answer for that. Maybe it was actually hit by an object, and that monk is the only person on Earth that either saw it or actually recorded it for history. Can we still get hit? You bet. I was at a conference out west, and Dr. Eleanor Helene was the only person that interested me. She was doing an asteroid study at the time, and she has been mapping about 3,000 Earth-crossing asteroids. They're still orbiting the sun, and they're in groups or families called the Apollo, the Aten, and the Amor asteroid families. All of them cross the orbit of Earth, and therefore any one of them is possible at some time in the future to wail on us. Yeah, NASA is capable of following an asteroid chunk as small as 2 feet now with their equipment. By the way, we wouldn't have to worry about an asteroid 2 feet across. It would probably burn up in our atmosphere, any one of them. Okay, the newspapers used to say, oh, we almost got hit by an asteroid. This one was 2 million miles away. Folks, that's 8 times farther than our moon, so I don't shudder when I hear that. I'd be worried if it came inside the distance between us and the moon. Now you're talking dangerous. And I don't know for those of you who read stuff in the paper, but even the Chicago Trib had an article that, according to scientists, without naming them, we had a 1 chance in 3 or something like that of being hit by, and they named the asteroid Apophis. Well, the Apophis asteroid does exist, but the person who published that with the odds, etc., was quite a bit less than that. It was 3% chance of being hit. And then after they refined the orbit even more, it went down to near 0. So you can sleep well. These are confirmed impact sites. And what it would look like to the casual observer, we get a lot more impacts in South America, and Europe gets a lot more than anybody. Wrong. This is where they were discovered by geologists. I don't know how many geologists there are in Chile and Argentina down here, but none have been discovered only because nobody's been looking for them. So Africa seems to be just the northern edge and a few in South Africa, but the middle of Africa, nothing. Again, nobody is looking for the asteroids and the evidence that can confirm an impact site. So by now, the volcanic origin is discussed as ancient history. And it took 35 years to actually get the evidence in the face of the people who believed they were volcanoes. And now we can all rest assured that impacts do happen, and we've been hit in the past and will be hit in the future. There's a nice simple crater. And a simple crater simply has a bowl-like dip into the surface. Not a whole lot of crater around it, because they're too small. Not much material was blown out, so you get relatively small edges of the craters. On Earth, 2 to 4 kilometers. On the Moon, 15 to 20. Why is it so much larger on the Moon? Less gravity. The gravity is 1/6 on the Moon what we are here, and since it's 1/6 as strong, stuff can fly out farther and all that good stuff. They even estimate the depth to the diameter is about 5.1, whatever units you want to measure. So it's 5 times wider and 1/5 as deep, whatever that may be. I actually had a trig problem in college from this crater, Copernicus. That's 83 miles across. I'm going to diverge for a second here, but I've got time, okay? If you and some friends want to tie yourself together and walk out to that crater, you're going down some of the roughest terrain I want to say on the Earth, no, on the Moon, to get down to the crater floor, which is 3 miles below the average lunar surface. So that is a heck of a hike. And since this crater rim varies between 2 and 4 miles high, it's really a 6-mile drop going down to the floor. Then you have about a 40-mile walk to these mountains that came as the rebound. Remember, we're talking about impact velocities going down, and there's a rebound effect with equal and opposite energy. Some of these are 3 to 4 miles high, and they're very steep edge. You would literally have to be an expert to climb those. And then you go down the other side, you got the same thing. 40 miles of crater floor on either side, and mountains almost too steep to climb in the middle. That is Copernicus. How many of you have seen it with a telescope? It's a beautiful target. That and Plato, I think, are my favorite targets on the Moon. They're also very big, easy to find. Okay, when we're dealing with complex craters, the crater walls collapse, and they get stair-stepped down, called terracing. And they have this central mountain peak, and relatively shallow. Now, these are 10 to 1 instead of 5 to 1. So they're much wider and not as deep as you would think. 10 to 1. And this is just a generic thing that I picked up somewhere. Seems to work. Diameter here is small. Diameter here is much larger. And all of this stuff we've already talked about at one point or another. No central mountain peak in a small one, but only the largest ones have those. Speaking of Plato. Now sometimes we can get even bigger. On the Moon, since they've been there for so long, fresh impacts on what used to be a smooth crater floor, that is now known as a walled plain, because it's got walls on the outside, or multi-ring basin, if that happens to be the case. Pardon me, I skipped ahead there. What we see here are fresher craters than the other one. So to a geologist, you use a principle of what's called superposition. A rock here, if there's something laying on top of it, that had to already be there, therefore it's older than the thing on top. And the higher up you go, the younger the rock is. And again, it can be dated to prove that. So this came after the big crater. It's laying on top of it. Again, that's relative dating. You need to take home some samples that you can date radiometrically to get absolute dating. And of course, that's been done with moon rocks. We got the first supply of rocks back from Apollo 11 I forget how many different ones. The whole Apollo program brought back 840 pounds of rock from different sites, but I forgot how many came from 11. Okay, here's a nice smooth area, and what you see here is went down, melted the rock under this impact, and it came upward and solidified, and it was very smooth, relatively speaking. Then this crater came along afterward, it's younger. Then this one's younger than that because it's laying on top. So that is one way to simply date a surface. This was in a space shuttle window. Didn't quite make it through the glass. Now we have pictures that show this powdery soil very well. I was wearing a t-shirt today that had that picture of the footprint on the lunar soil. Technically not soil, called regolith, but it's all powdery. And it's powdery because it's been bashed by micrometeorites for billions of years. In fact, that became a problem. Astronauts wanted a better way to get the dust off their uniform because they take it back with them into where they sleep, and it gets all over equipment. It's a mess. And I don't know that NASA has solved that problem yet. Mini vacuum cleaners, maybe. Okay, the moon and Mercury. No atmosphere, nothing to slow down the impactor. They hit the surface, since you're not going to burn up. The small objects will burn up or break, and once they are made, processes of erosion happen, but it's very slow. The rocky planets in our solar system are the ones closest to the sun. Everything made mostly of gas are further out, and we go out to 30 AUs, which is where Neptune is. That's a huge area out there. There's very little evidence that anything ever hit one of the gas giants, although I did see one. I was on a sand hill in Nebraska, I forget the year, but it was probably 15 years ago, and one of the guys who helped create the star party came running up and he says, "Put your telescope on Jupiter. NASA just reported something." And what they reported was a collision between something and Jupiter. But it happened on the other side of Jupiter. So as it slowly rotated around, we picked it up, and I saw some black smudges in my 14-inch scope. Those black smudges were an explosion of whatever hit Jupiter burned up right then and there. Yeah, we have greater impact velocities the closer you are to the sun. Remember one of, what's his name? Again, brain issue. Kepler, Johannes Kepler, one of his laws says objects speed up as they go toward the sun in their orbit, and they slow down as they go back out. Well, they're at their greatest velocity in the inner solar system, and that's why rocky planets like us, Venus, Mars, and Mercury, are liable to get damaged pretty well. Okay, again, here's Highlands and Maria. And by the way, I know I have a better picture of this, and I think I'll wait and describe that later. This is a terrible slide. This area, I don't know why I included this area, there's no date at all, so they don't fudge it. Oh, I think it might be the same as, no, they don't do that, they just leave it blank. But they're trying to show round craters, and you really have to get close to see all these craters. Almost all are perfectly symmetrical round. Here's the one I wanted to show you. This is the right-hand side of the Caloris Basin on Mercury. And this was hit by something huge, melted, I believe it's 1,300 kilometers in diameter. It's a huge feature for a small planet. And the shock waves went through the planet and messed up the far side. It would be like the antipode of where the impact site was. And it's called jagged terrain on the other side of Mercury from this Caloris Basin. And the word Caloris, of course, means heat, and there was probably a lot of it involved and maybe melted a good chunk of Mercury. Lava plains covered up by craters. And now, a warning to your own species. See, this instructor here is taking claim for their kind invented the iridium bomb. I think that's cute. Beware of this. Now, we have to go back to the late 60s when previously mentioned Lewis and Walter Alvarez had some hint that there may be a giant crater suggesting an impact down in the Yucatan Peninsula. This is a geologic map and a poor one, but roughly color coding. The colors pertain to ages, okay? And this is a better one. This is the actual boundary of the Yucatan. This is land from here down. This is Gulf of Mexico, Gulf of America, whatever you want to call it. All the white things are drill cores. And you can see a multi-ring basin developed, and they have taken a lot of shots at trying to determine how this happened, and they mapped it in side view. So with the profile, these are kilometers, I believe that says. So it went down a kilometer deep, and this is roughly 120 miles across here. So that's a pretty good sized crater. But as I've discovered just in the last month, there are 3 or 4 that have not been confirmed yet, but they're larger than this one. One is in Canada, and it's not Sudbury. It's way up where the Franklin Mountains were first created. Nobody's ever heard of them because they're gone. The Franklin Mountains were east-west across northern Canada, now eroded. But up in that region, way up in what's known as the Canadian Shield, which is bedrock coming up from underneath, there was a huge crater there that was approximately 200 miles across. Okay, it's gone with erosion, with a whole mountain range gone. But this did a pretty good job on the dinosaurs.
Is that a gravity map?
Let me see.
It's from Pemex, I think.
Yeah, this is not gravity, although they certainly do that. They just take a ship along the shore and measure the gravity all the way along, and they can do cross sections any way you want. But that is not actually a gravity map. I can't read that. Chesapeake Bay, have you ever heard of that? This is the Delmarva Peninsula, Delmarva, Delaware, Maryland, and Virginia. That's where they get that term. And right on the end of this south point on here is pretty much the center of what used to be a very large crater. And of course, drilling is required to determine that. This is the this is one of the round lakes in Canada in the Canadian Shield. Manicouaguan is its name. It's famous for fishing now. Weren't any fish originally, but somebody decided to put some fish in here. It's a round lake with some spurs on it, and nothing to cover it. No trees. Is too far north. Trees can't grow there, but it is a huge crater. There's another one I don't have a picture of in South Africa. That's called the Vreede Fort, and the one you were talking about in Western Australia. These may be in the top 5 as far as the largest craters to hit that we know of and can measure. And here's another one. This is in Des Plaines, Illinois, folks.
Is that under the airport?
I'm not sure where the airport is, but in Des Plaines, this is the oldest rock. And here the rock has been pushed up in the middle, just like the rebound on other planets, etc. North here, south on that side. This is miles. So it's a 12-mile or so function, all underground. You can't see anything if you're driving around that area. But the geologists have mapped the strata of the rocks and brought up rock cores, and they know that that used to be an impact site. But it's nowhere near as large as some of the other ones. It's just our local one. Okay, so when we talk about getting hit by some kind of an impact, could be an asteroid, could be a comet, could be a UFO, who knows? That was a joke, by the way. Okay, just want you to know. Here are different terms. Gardening is just basically micrometeorites. Small cratering. Now, this is another term in geology. A lot of people aren't familiar with that. Mud flows would be an example of mass wasting. It is sections of the earth that are moving downhill only under the force of gravity. Nothing else is causing them to slump down there. Now, I believe it was you who was talking about an object being hit and broke apart into 7 pieces, etc. Okay, that may not happen here, but Eugene Shoemaker had evidence of an asteroid that had been broken apart. One of the sides had rotated, and then it kind of glued itself back together. And it still has, I think it's Iapetus, has a ring around it that sticks out. That's for large cratering. Now we keep getting bigger. When the crater exceeds the target size, you're going to blast it. We'll go into fragments. Realignment of spin vector simply means you've got a new north-south pole you're going to rotate on. And then catastrophic. This would completely shatter the object and may have been helpful in forming the asteroid families I talked about earlier. Okay, I'm not going to read this to you, but take 2 minutes and read this. This is if Chicago was hit with a 10-kilometer asteroid. This term blast radius may not make a whole lot of sense, but if you have a blast radius of 4,000 kilometers, that means roughly 3,000 miles away, trees would ignite instantly from the heat. And trees explode when they catch fire in this case, not slow burning. Not even like what the forest fires we've had in California and now the Carolinas. They just explode. A lot of this information came from climate studies. Some of it from computer studies. It's a whole lot easier to simulate stuff on a computer than to build a model and try to explain all of this stuff. But we're talking down in this area for centuries, we would not be able to see the sun. Too much dust. Nuclear winter, it's been called by Carl Sagan and many other people. Plant growth stops, extinctions of animals, basically wait 2,000, 3,000 years, and if you're lucky, you can start over again. Now, estimated frequency of impacts on Earth. This goes from once a month to every 100 million years. And across the bottom, we're dealing with megatons of essentially dynamite. TNT is the ingredient in dynamite. A megaton, that'd be 1 million tons of dynamite. Okay, that's here. This is somewhat logarithmic, going from 100 to 10,000 to 1 million. And we get down here to some fairly earth-shattering, pun mentioned there and meant. KT impact was when the dinosaurs got wiped out 100 million years ago, less than that, about 65, 66 million years ago. But, you know, can it happen? Yes. What are the odds? The odds are near perfect that at some time in the future we're going to get hit with an asteroid. We don't know how big it is. We hope it's not big, but hope it doesn't really stop asteroids. So about 5 years ago, NASA sent up what's called a DART experiment, and they purposely ran into a small asteroid. I believe its name was Didymos. That's right. And it did break off a chunk. But what they were really trying to do is see if they redirected that asteroid. Even a half a degree would be enough. If we had the lead time, 3 years, 4 years, a half a degree would miss our little dinky 8,000 mile wide planet. So it was a successful thing, but I think a larger mass would be more effective at the same speed. But again, velocity squared, so you want to go fast and run into that thing,
Depends on composition.
of course. And if what they found was that it wasn't specifically the DART mission, but some comets are made out of not solid material, but groups of rocks with spaces in between them. So the impact of, say, a hydrogen bomb on that, it would tend to absorb it and not be blown apart as badly as if it were a solid, like, you know, the Bruce Willis movie from 15, 20 years ago. Oh, speaking of new, gravity studies and drilling through the ice found a very large crater underneath the ice in Antarctica. The longitude is 120 degrees, whatever that means, nothing to me. However, this is the size of the Chicxulub. So if you kind of compare them, this would have been between 4 and 5 times larger than the Chicxulub, which wiped out the dinosaurs. So this was probably back a billion years ago or more. And as long as it's been ice covered, it took scientists, I believe, about 2011 to find that. So that's what, 14 years ago? We didn't know. And I suppose we're going to continue to find things we don't know about. So, question, could Chicago look like this in the future? The answer is unfortunately yes. It's possible. Highly unlikely, though. NASA can find all kinds of junk out there with their radar, and they're looking. But as I said before, they have equipment now that can pick up a 2-foot wide chunk of rock, technically a meteoroid, not really big enough to be an asteroid. So it's going to be hard for us to run into a big rock, but if we do, hold your breath, because it's going to be tough. Okay, I do have a little thing that's kind of fun to play with. This at Purdue, Impact Earth is the last part of that. And what you can plug in a couple of masses and velocities, and it'll tell you the results of a collision like that. And these little games are kind of fun to play with. I think I spent 35 minutes before I had to go and tell my son, hey, you got to see this. He's into that sort of thing. He likes to play running one thing into another at high speed. So, Purdue, thank you. That is it, folks. Any questions?